Right, this is lesson 2, transformations of functions. Our essential question is, what do the differences between the equation of a function and the equation of its parent function tell you about the differences in the graphs of the two functions? Okay, so this is what we're going to be learning about. We're going to learn about translating functions, reflecting functions, stretches and compressions, graphing combinations of functions, identifying those transformations, writing an equation, and of course, a summary of everything we've learned. Right, translate a function. So translations of functions are very similar to things that you probably have already seen. So we're talking about reflections, rotations, and transformations. So a translation is a type of transformation, one that shifts each point on a graph the same distance and direction. Okay, so I want to graph the function f of x equals x squared. So anytime I see just a number or a letter, so like f of x equals x, that's a parent function. So x squared is a parent function. And I want to graph it for the domain of -2 to 2. The graph of g is the graph of f after a translation 3 units down. Okay, so I'm going to take every one of those points and I'm going to move it 3 units down. How are the equations, domains, and ranges of f and g related? So the first thing we want to do is we want to graph the function. So once I've graphed x squared, which is the parabola, because it's a quadratic function, okay, with the given domain. So I start at -2 and I end at +2. So that's my domain for my function. So I don't go any further past that for my x's. So I need to create a table to graph the function. You can do that. I can pick any points. So I can do -2. So -2 squared would give me 4. So that's how I'm graphing those points. Also notice the brackets, which means those points are included. Okay. So the next thing I need to do is I need to move each one of those points 3 units down. Okay. So I start again with this red function here. And I'm going to move each of those units 3 units down. So I create this blue function. So one way you could do it is by taking the original y value and subtracting 3 from it. So 4 minus 3 gives me 1. So that means it's going to be at 1. Okay. The domains of f and g stay the same. Okay. I didn't move side to side. I just moved up and down. My range is going to change. My range for my original function was 0 to 4. Okay, so the lowest point on that graph was 0. My highest point was 4. But when I moved it down 3 units, everything got shifted down, which means my new range is -3 to 1. Okay, so each point got moved down 3 units. You can see this red to the blue. Okay, so each one got moved down 3 units. So it's a vertical translation of f of x. So now I want to graph the same function, but I want to translate it 3 units to the right. Okay, so I want to know how their equations, domains, and ranges of f and g are related. So again, I graph this function. Okay, and again, I want to move each point right 3 units. So again, I start with this red function here, and I'm going to move everything over 3 units. Okay, to create that blue function. So the domains of f is -2, 2, what they gave us, while the domain of g is 1, 5. So notice I went from -2 and I added 3 to that, which got me 1, and 2 plus 3 gives me 5. Okay, the ranges of f and g are the same. Okay, I didn't move up and down, I moved side to side. So each point x, y moved right 3, which means that the x minus 3y, in general, g of x is f of x minus whatever you move. So if I moved 3 units, this is actually going to be +3. Okay, reflecting a function. You can have reflections across the x or the y axis, or you can have them across a specific point. So I want to graph f of x equals 2x minus 3 and its reflection across the x-axis. So if you want to think about it as a piece of paper, right? And the x-axis is in between here. So if I fold that down, it's going to be a mirror image of each other. Okay. So the first thing I want to do is I want to graph this function. Okay. The next thing that I want to do is I want to reflect points over the x-axis. So each point x, y will become x negative y. So 0, so this pink one, 0, negative 3 is going to become 0, positive 3, and 2, 1 becomes 2, negative 1. Okay. And then I connect those two new points. So we can see that all of the signs in the new line are changed. Okay, so instead of 2x minus 3, I have negative 2x plus 3. So I have a slope of negative 2, which means I went down 2 to the right 1, and I cross my y-axis at positive 3. Okay. So I want to use that same graph, and I want to reflect it across the y-axis. So like x-axis went this way, y-axis is going to go this way. So I'm going to flip it so it's got a reflection across the y-axis. Okay. So since I changed, when I cross the x-axis, I changed the y values. When I cross the y-axis, I'm going to change the x values. Okay. So first thing I want to do is I want to graph this function. Okay. Then I want to reflect the points over the x-axis. So notice that x becomes negative x. So my new points, right? This point goes here. This point goes here. Okay. So I connect those new points. And we can see that just the slope changed. The y-intercept does not change in this case, but the slope changes. So I went from positive 2x to negative 2x. Stretches and compressions. Okay, so stretching or compressing, I'm just figuring out if it's going wider or if it's going smaller. Okay, and that's both vertically and horizontally. So I want to graph f of x equals the absolute value of x with domain negative 4, 4, and g of x equals 2 times f of x. How are the domains and ranges related? So the first thing I want to do, of course, is graph my original function. So it's an absolute value function, which means it's a V-shaped. Okay. Next, I'm going to make a table because it makes my life easier. So these are the originals. These x values are the original that I put in and what I would get in for my original equation. Then I multiplied each one of those answers by 2 because it was 2 times whatever value I got for f of x. So this became my new set of equations. Okay, from here, I'm going to graph these points right here. Okay. So I graphed my new points and I connected them. Okay, so the domains of f and g are the same. So the same x values I'm still using from negative 4 to 4, but my range has doubled. Okay, so I've multiplied it from the original range of 0 to 4 to 0 to 8. Because 0 times 2 is 2, or 0 times 2 is 0, and 4 times 2 gives me 8. A transformation that increases the distance between the points of a graph and a given line by the same factor is called a stretch. Okay, so the graph of G is a vertical stretch of the graph of F by a factor of 2. So next I want to do the same thing, but I'm putting the 2 inside the parentheses this time. Okay, so that's going to change it slightly. So again, I'm going to use my exact same, okay, at negative 4. I'm going to plug those values in, okay. I graph my new points. And then I connect those points. So the ranges of f and h are the same. Each x value is 1/2 the value of its previous value. So the domain of f of x equals negative 4 to 4, while in h of x, it's negative 2 to 2. Okay. A transformation that decreases the distance between the points of a graph and a given line by the same factor is called a compression. So the graph of H is a horizontal compression of the graph of F by a factor of 2. Okay. So you can have both horizontal and vertical stretches and compressions depending on where the coefficient of K is located. So for example, right, I have f of x equals x cubed. That's my original parent function. When it's inside the parentheses, it's a horizontal compression because I've squished it, but it's still going this way. Okay. When it's outside the parentheses, okay, when it's inside the parentheses, but it's less than, it's between 0 and 1, it's a stretch. Okay. Then when it's outside the parentheses, so 5x cubed is a vertical stretch, while 1/5 is a vertical compression. Okay. So horizontal is inside the parentheses, vertical is outside the parentheses. Okay. Graphing a combination of transformations. This right here tells you exactly where everything goes and what everything relates to. All right, so I want to graph y equals f of x, okay? And I want to graph the transformations of these functions. So I'm looking at this function, my original function, and I want to change it to this function, okay? So I notice that there is a negative sign out front and this +2, okay? So that +2 tells me I'm moving everything to the left, and the negative sign out in front tells me I'm flipping it across my x-axis. It's going to reflect it, okay? So I go ahead and move everything, because that was in parentheses, I'm going to move it everything to the left 2 units. So from here, I went to the green, green, to the green, to the green, okay? Then I'm going to reflect that across the x-axis, okay? Which gives me this pink down here. All right, so the next thing I want to do is I want to graph this equation, y equals f of x, to y equals 1/2 f of x plus 3. So again, I want to figure out what my changes are between my original equation and my new equation. So the first thing that I notice that changes is the 1/2 out in front, okay? The +3, which is outside the parentheses. Those are the two things that change. Okay, the 1/2 out in front tells it's a vertical compression by 1/2. And the +3 on the outside of the parentheses tells me I move the entire function up 3 units. So again, I'm still following order of operations. So I want to do the multiplication first and then the addition. So I'm going to multiply each of these points by 1/2. Okay. So instead of 2, 2 times 1/2 is 1. So there's my new point. 4 times 1/2 is 2. 3 times 1/2 is 1.5. And 7 times 1/2 is 3.5. Okay, so that's where I'm getting those points from. And then I move everything up 3 units. So that's my orange. So next I want to identify the transformations from an equation. So again, I'm going to use this transformation of functions to be able to figure out what changes. So you always start with the parent function. So in this case, what transformations of f of x equals x squared result in the graph of the function g of x equals -1/3 x squared? Okay, so again, I'm looking for the difference between x squared and -1/3 x squared. So I notice that there's a negative sign outside the parentheses, and I notice the 1/3 is different, and the 1/3 is inside parentheses. So I figure out what those differences mean. The negative out in front tells me it's a reflection over the x-axis. while the 1/3 represents a horizontal stretch by a factor of 3 of 1/3. So I'm basically squishy, or like making it go bigger. Okay. So then the green was what the graph would look like. Okay. So this green is that horizontal stretch. Okay. The red is the reflection. So again, I want to translate transformation. I want to figure out what my transformations are. So I'm going from x squared to x minus 4 squared plus 5. So again, I notice that there is a minus 4 inside the parentheses and a plus 5 outside the parentheses. The 4 inside is translated 4 units to the right. The plus 5 tells me I'm translating 5 units up. I do what's inside the parentheses first. Okay, so I'm going from blue to green and then green to red. Writing an equation from a graph. Okay, so you're thinking about what changed. So example, a scenic train ride makes trips on an old mining line. The graph shows the distance in Y kilometers of the train from the station X minutes after the ride begins. What equation represents the distance from the station as a function of time, and what is its domain? So I'm looking at this function. It's an upside down V. Okay, we know that V's are absolute value functions. Okay, but we also know that V-shaped functions stand straight up. They look like an actual V. This is an upside down V. So that means there's a reflection somewhere. Okay. So it's a V-shaped graph, which is an absolute function. Okay. And then I'm determining the types of transformations. So I know that an absolute value function starts at 0, 0. Okay. That's my vertex for that function. But this one is at 15, 15. So there has been some sort of reflection. There has been a vertical translation and a horizontal translation. Okay. I can use that information then to figure out what my new function actually is. Okay, so I'm going to substitute what I know. So the general form of an absolute value function is f of x equal a absolute value x minus h plus k. hk is your vertex. Okay, so I know my vertex is 15, x equals 15, and y equals 15. So h equals 15, k equals 15. Okay, then I can pick any other point that I want, and I can substitute it in for x and y. Make your life easy. Do 0, 0. You can do 30, 0, but it's going to be bigger numbers for you. Okay, it'll give you the same answer, but it's going to give you bigger numbers. Okay, so I'm going to use 0, 0. So I put 0 in for y, or f of x, and I put 0 in for x. Okay, now I'm solving for a. So when I do this, I'm going to add 15 to both sides. Okay, I'm going to simplify the absolute value. 0 minus 15 is negative 15. The absolute value of negative 15 is positive 15, but there's still that negative sign out in front. So I have negative 15 equals negative 15a. I divide both sides by negative 15, so a equals 1. I substitute that value back into my original equation. So I get f of x equals negative 1, absolute value of x minus 15 plus 15. Okay, so the domain is our x values. So this means that we have a domain, if I look at my graph, from 0 to 30. I can't go past 0, right? Because time is not negative. And the train returns 30 minutes later. Okay. So again, transformation of functions, this is really your summary. So you have your y coordinate, that's where you start. Equals, if you have this negative sign out in front, that's a reflection across the x-axis. Your a is a horizontal stretch or compression, vertical compression, okay, depending on what it is. If a is greater than 1, it's a horizontal stretch. If it's between 0 and 1, it's a vertical compression. Okay. If sorry, that should say vertical. F function must pass the vertical line test, otherwise it's not a function. You're going to reflect across the y-axis if the negative sign's inside the parentheses. B is, again, your horizontal compression or stretch. Okay, if it's greater than 1, it's a horizontal compression. If it's between 0 and 1, it's a horizontal stretch. Your x coordinate, and then h plus h tells me I shift to the left. Minus h tells me I shift to the right. Okay. Plus k at the very end, that tells me if I go up or down. Plus means I go up, minus means I go down.